Okay, good morning everyone. Well, it's my pleasure to introduce our next speaker for this session dedicated to neutron and gamma rays in fission. Well, that's our chairman, so I don't know. Dr. Keegan received his PhD in experimental nuclear astrophysics from the University of North Carolina at Chapel Hill in 2016. He started as a postdoc at Los Alamos, working with both the KNU and DANCE project at Lens the same year. Since then, he has served as a PI for the KNU PFNS measurement project and has since initiated a broad neutron scattering measurement campaign as PI of the Cognac project at Lens. Cognac is a great name. Built from project awards from LANL LDRD, that's kind of internal competition in Los Alamos, NH22, which is non-proliferation, and a recent DOE Early Career Award, which is a very prestigious award. So, please.
Thank you very much. Is positioning of the mic okay?
Yes.
Okay. Well, it's an honor to be able to speak to you about fission, neutron, and gamma ray experiments today. I'm going to try to cover quite a bit of material, some in more detail than others. And so just to briefly outline the two sessions that I'll try to cover today, we'll talk about some history of N-gamma emission and talk about prompt fission neutron spectra and mean energies of those distributions, and then going into neutron multiplicities, multiplicity distributions, and average neutron multiplicities. And then correlations of nubar with kinetic energy and other fragment properties. And then neutrons and gammas generally have kind of a similar analogous set of observables that you can see, being the prompt fission gamma spectrum, gamma multiplicities, multiplicity distributions, and average gamma multiplicity. And then those as well have correlations. And then we'll talk about some NN correlations and some models for describing these spectra. And so that's all going to be part one, just giving you a brief crash course of what can be observed and what has been observed and what we think we know. And then going on to session two, that's where we'll get into actual experimental techniques, what matters, what can hose your whole experiment, and what you really need to consider when you're thinking about measuring these quantities. And yeah, at any time, please interrupt with questions. I'm happy to answer anything during the lecture. Okay, so briefly on the history. This is a plot from, if you want to learn more about the history of the Manhattan Project, then you can go to one of these two papers by Chadwick and Capote, giving you a very good history of what was known at the beginning of the Manhattan Project and how it evolved throughout the course of the project. One thing that was clear right from the beginning was that uranium and plutonium are two very important isotopes to focus on for, yes, sufficient, thank you. All right. Two very good, two ideal elements to focus on for making a nuclear weapon. And so what we have here on the y-axis is optimism. So how people thought, how people felt about these two elements, and specifically U5 and Pu9, in terms of making a nuclear device. And yeah, initially plutonium was discovered at the beginning of the Manhattan Project, and so there wasn't much optimism. And so a lot of initial research was relating to uranium. And then as things went on, plutonium had enthusiasm grow until people realized, oh wait, Pu240 is a problem. It makes a lot of alphas and spontaneously fissions as well. And so optimism dropped. It was a bad few months for plutonium there. And then later on, people realized actually with the implosion method, we can use plutonium for these kinds of devices. And so plutonium skyrocketed back up until the Trinity test here on July 16th, 1945, and the rest is history, yes. Well, chain reactions are initiated by fission. So if you have a spontaneous fission, you could have a spontaneously exploding bomb. Yes. Short answer. And so one thing that's, so of all the observables that we've talked about this week, the fission cross-section, fission product yields, and now fission neutrons and gammas, not that it's a competition, but neutrons are the best, and I'll tell you why. Before there were LAUR numbers, like we have to put on all of these Los Alamos documents here, there were LAMS numbers, Los Alamos manuscripts. LAMS1 was uranium-235 prompt fission neutron spectrum measurements. And so these are some of the earliest measurements from Rice University in Houston, Texas, Liverpool University in Great Britain, and a fit to the spectrum drawn by hand here. That's what we thought we knew at the time, and here's what we know now. And so now in these other data points, here are what we believe we know now, or NF 8.0 is now a slightly outdated version of what we think we know now. And then I'm showing some Kainu data here for 1.5 MeV incident energy on uranium-235. So this is kind of how the history went. We thought we knew something for the PFNS, the cross-section, nu-bar, and other quantities, and these all kind of had different trajectories that flowed throughout the Manhattan Project. Initially, we thought the cross-section was a lot higher than it actually is. We also thought nu-bar was a lot lower than it actually is. And all of these things kind of balanced out to get to the point that we were able to make the first nuclear device at the end of the Manhattan Project. And another reason why neutrons are the best is because while fission is interesting, a nucleus fissioning into two different daughters, highly excited, highly deformed, all kinds of different dynamics going on with the kinetic energy and the excitation energy. If there were no neutrons, I don't think we'd be sitting here right now, because it's the neutrons that really drive this chain reaction, which is why Pu-240 was such a big problem. And so, yeah, it's these neutrons from fission that drive the next step in the chain reaction, which drives the next step in the chain reaction, all because of these neutrons. And so there's been a lot of focus on the neutron energy spectrum and numbers of neutrons from fission, because it's highly critical for understanding how things work in a fissioning system. And so here I'm showing an example of, tomorrow you'll hear a lot about you'll hear about integral benchmarks and critical assemblies. This is one example, the Jezebel assembly, basically a bare plutonium sphere. And we know by setting up this experiment that this sphere is critical. It's at criticality 1. It's making as many neutrons as it's losing. And so it is balanced in that sense. However, when you put this into MCMP, which is actually only 3 lines of code in MCMP, not a coincidence, then you can put this in MCMP and calculate your criticality of your system, and you'll find out that you do not get criticality 1. Even though we put in our best understanding of all these different cross-sections that matter, I'm showing here contribution to the relative standard deviation on the y-axis for different reactions that can occur on Pu9, elastic and inelastic scattering, N2N and 3N, fission, capture, nu-bar, and the PFNS. We have various levels of uncertainties on all these quantities, and so this all goes into understanding, it goes into a confidence level in how well we think we understand these kinds of systems. Fission cross-section, even though we know it to 1 or 2%, contributes a lot to the standard deviation, as well as the neutron multiplicity and the PFNS. Conversely, elastic and inelastic scattering, which are on the topic of this conference, also very interesting, have on the order of 20 or 30% uncertainties or more. And so we know these very well, and they still make a huge difference in the standard deviation. We know these relatively poorly, and they have a similar level of contribution. But we'll hear more about critical assemblies tomorrow. Okay, timescales. So we've seen similar plots like this a few times throughout FIESTA, and we're operating in this regime where we've created our fragments already, and now we're emitting the prompt neutrons and gamma rays. Neutrons are emitted on the order of 10 to the minus 18 seconds. Gamma rays are afterwards, usually on the order of 10 to the minus 14 or minus 7 seconds. And to give you a feeling for how this happens and why it is, we've seen plots like this as well, including yesterday by Toby. The fission fragment, once it's initially created, is in typically a highly excited, highly deformed state. And if you have enough excitation energy to be above the neutron separation energy here, then the nucleus will want to just throw away neutrons, emit them first, so that you can get down to the point where you're losing as much excitation energy as possible and trying to get down to your lowest excitation you can towards the ground state if possible. And then once you pass down below your neutron separation energy, you can't emit any more neutrons, and so now you still want to emit as much energy as possible, and so we get higher energy gamma rays that are more of a statistical nature, smoother spectrum, higher energy spectrum that we'll see in a little bit. And so you get down to this ERAST band down here, ERAST line, which is the minimum excitation energy for a given spin and parity. Spelled YRAST, pronounced ERAST because of Swedish origins, I'm led to believe. Maybe that's not true, but so this is where things stand for our understanding of why neutrons come first, then gammas, and what kind of neutrons and gammas we expect. As another view, this is actually from an N2N type paper, but a similar concept applies. You can go emit your 2 neutrons in this step or this step. If you're emitting 2 neutrons, it could be in fission 1, 2, 3, 4, 5, 6, 7, or 0 neutrons. And then gamma rays emitted in different fashions over here. And on each slide, if applicable, I left some citations up here. So when the lecture is available, if you want to read more about any particular slide or any particular topic, look up the references there. Okay. And then in terms of, yes, 2 questions.
Sorry, but fundamentally, why neutrons really come first and gammas after? Why can it be like sometimes randomly first gammas and then some neutrons?
Quantum mechanical probabilities of emitting particles from the nucleus versus gamma rays, it just is a relative probability argument. So once you have enough excitation energy to release the neutron, it just wins. I don't know enough to write out the equation to describe that, but it's a relative probability argument.
Okay.
Yeah. Yeah, it's always a competition as well. So nothing's ever 100%.
Yeah, sure.
Yeah, yeah.
Here's a question.
Go ahead.
So, related to this figure that you have on the screen right now, it seems like the same argument would apply for proton emission as well. If you have a certain amount of excitation energy, shouldn't you be able to find the proton as well? Suppress?
I believe it's related to the kind of nuclei you create. You have highly neutron excessive nuclei from fragments. And so you have a lot more excess neutrons than you would excess protons. Yeah.
I have a question. I think I see a hand up to you.
Yeah, if there are additional comments on that as well. You had a,
Thank you very much for asking questions.
did you have a comment you wanted to add as well?
Sure.
Yeah.
So for the protons that are blocked by the Coulomb barrier, I think that's probably the main reason. And the neutrons, I think, if you want to be really crude about it, you could say that the strong force is stronger than the electromagnetic force.
Yes, thanks. Okay. We've talked about different varieties of chances of fission and pre-equilibrium neutron emission in fission. And so this is a similar description of these processes, and I'll kind of add my own variation onto it. So the typical path of fission is first chance fission, where you have an incident neutron capturing onto, in this case, a Pu9 nucleus to create a Pu240 nucleus, creating some two representative fragments, which then emit neutrons and gammas. So this neutron has captured, equilibrated to make an actual Pu240 nucleus. In second chance fission, we still create this Pu240 nucleus, but there's enough excitation energy left over in Pu240 to boil off this neutron effectively before the fission occurs. And so instead of a Pu240 nucleus fissioning, it's a Pu239 nucleus. And that changes the character of the fissioning system, therefore also your fragments. And the fission carries on from there. Third chance fission is very similar. We still create this Pu240 compound nucleus, get to Pu9 after a pre-fission neutron emission, which then emits another pre-fission neutron, similar character, also low energy. We saw yesterday that these pre-fission neutrons here in the different chances of fission are generally lower energy than the PFNS from the fragments after acceleration over here. And so you get a second feature like this, leading to a Pu238 nucleus fissioning. Pre-equilibrium neutron emission is very similar in nature, in some sense, to second chance fission, in that you're emitting one pre-fission neutron. However, this is more like a neutron scattering reaction occurring on Pu9 before the fission occurs. You never actually form this Pu239 compound nucleus. And that's really the fundamental difference. And the difference there that you can observe then is that this pre-fission neutron from pre-equilibrium neutron emission has a much different character. It has a more forward peaked angular distribution. The energies are very different than what you'd expect from a pre-fission neutron from second and third chance fission. And so while they look similar, observationally, they are very different. And in a theoretical description, these are also very different processes. However, as you reach the point where you're crossing between this threshold where you can have pre-equilibrium neutron emission or second chance fission, there's a competition. Experimentally, when you measure the PFNS as you go through these processes, it looks like a continuous shift from the second chance fission peak into maybe I should just go to this slide. Oh boy. Well, we won't see the 1 to 1.5 MeV PFNS. That's okay though. So what you see is that this axis down here for a second chance fission, this is the low energy neutron emission from the second chance fission when you actually form this Pu240 nucleus. As you go up higher in energy, this peak effectively morphs into this forward peaked pre-equilibrium neutron emission peak. Yes, question?
So, also, the excitation of the system after the...
Wait for the microphone, yeah.
So, apart from the neutron differences of the these second chance and the pre-equilibrium, I guess that the excitation energy that you leave the compound nucleus will be different, no?
Yeah, the different processes. So the residual excitation of the nucleus, and therefore the fission afterwards would be different as well.
So
I don't know the details of how they're different, though.
Yeah, that was
Yeah.
my question, because maybe with the mass distribution or something, also you could further disentangle those processes, or no?
Possibly. Yeah, I don't. Yeah, I don't know. So.
Okay.
Yeah. Experimentally, what we observe is that these neutrons all combine into one spectrum. And so
Because
you're asking a fission neutron
neutrons-
experimentalist how the,
Only with neutrons seems
Hmm?
complicated, only with neutrons, apart from knowing that they are picked at one point.
knowing the neutrons seems complicated. Was that the
No, to disentangle both.
Yeah, it is indeed complicated. We did have so one point I'll make too is that while there are, these are, when we say PFNS, we say prompt fission neutron spectrum, meaning neutrons emitted promptly from fission. Those are these neutrons and these. These pre-fission neutrons are not technically promptly emitted from fission, they're pre-fission, but they're so hard to disentangle from post-fission neutrons that the PFNS is generally described including the pre-fission neutrons as well, even in evaluations. If you look at NDEF and JEF and GENDL evaluations, they have the pre-equilibrium neutron emission features in them if they've included that physics in there. Even though it's pre-fission neutron, it's included in the post-fission. So we did have one effort where we tried to identify more details about the pre-equilibrium neutron emission here, and there'll be a reference later on this. But it effectively amounted to fitting this peak in the spectrum and looking at the angular distribution of neutrons that we knew were from pre-equilibrium neutron emission. And it follows exactly what you'd expect for a theoretical model of what the pre-equilibrium neutrons should look like angular distribution-wise. So we've been able to see things like this, but did that help anything? Okay. Okay, and then, so then here, now you have a competition between this pre-equilibrium neutron emission, second chance fission, and also third chance fission over here. In this case, for plutonium-239, I'm showing all these spectra I should mention as a ratio to a Maxwellian, which has been done a few times in the past as well. A Maxwellian distribution, which we'll see in a little bit, is it contains most of the energy dependence of the fission neutron spectrum. And so if I were to show you these three, supposed to be four, these three spectra on the same plot, you would have a pretty hard time telling some of the differences between them. They would look mostly similar. But we divide out the Maxwellian nature of this, and so you see a lot of these fine details in great detail. And so a factor, some numbers I like to keep in mind are that below about 400 keV is about 10% of the PFNS generally, and above 4 or 5 MeV is another 10% of the PFNS. That means within this half MeV to 4 MeV region, that's 80% of your PFNS in this small region right here. So keep that in mind when we're looking at these spectra as well. Okay, and then at forward angles, you get a much higher peaked pre-equilibrium distribution. And then as a 3D view of what this looks like, incident energy on this axis here, outgoing energy or PFNS energy, and then the value of the PFNS, you get to see some of these shape changes as they evolve. And so first chance fission here, second chance fission leads to a decrease up here relative to the lower energy excess, which then folds into this pre-equilibrium neutron peak that takes over at high energies. And this is again ratio to Maxwellian. Yes?
I'm a bit confused about what the PFNS axis really mean there.
It's relative probability. The PFNS, the prompt fission neutron spectrum, is a shape.
So what does it mean to have 1.8?
That means 1.8 relative to 1. That's the ratio of the neutron emission energy that you would expect for those two energies. It's a probability distribution.
Ratio of energy or ratio of number?
Ratio of number.
Number of neutrons
At that energy, yeah. So if you had a PFNS of 1 at 5 MeV and 0.5 at a different energy, then the ratio that you should expect a factor of 2 more neutrons at the first energy as opposed to the second.
Okay.
It's just probabilities. Okay.
But it's a ratio to Maxwellian.
But this is a ratio to a Maxwellian, yeah. Okay. So you'd have to multiply through the Maxwellian to get the 4 more probabilities, I guess, yeah, but yeah. No.
To integrate to one. You force like the integral to be one, like a proper PDF.
So over all energies, so in this plot, no. But over all energies, the formal PFNS should have an integral up to 1, yeah. Yeah, yep, yep. Fun fact, when you produce data that go into nuclear data evaluations, a lot of times they're treated as shape data, which then comes along with an arbitrary normalization factor to make things agree at different energies. And so, yeah, you're all asking fine details about questions that would set the scale for these spectra. No matter how much effort we put into that, I can guarantee you that effort would be thrown away because it would be shifted in some other way. But yeah, relative probabilities is what the PFNS actually describes. Okay, and then descriptions of the PFNS, the simplest and most commonly referenced is the Maxwell-Boltzmann distribution, or Maxwellian, shown here. And you might recognize this from a number of different places, astrophysics, statistical mechanics, and other places. And this very roughly describes the PFNS, roughly enough that we can divide by it in those spectra I just showed you to get rid of a lot of the temperature dependence. And yeah, some assumptions though are that you're emitting the fission fragment is at thermal equilibrium, and so you have a statistical neutron boil off. The fragment excitation energy doesn't exist, and there's no center of mass motion. So these are some pretty important deficiencies of this kind of description, and so that's why we use it just for kind of ratios, because it's simple to say I did a 1.5 MeV Maxwellian or 1.3 MeV, because everyone knows what you mean, and there's even a simple way to get the average energy of the spectrum from the temperature. But we know this is insufficient for even the simplest fissioning system. Spontaneous fission is even too complicated for this. Watt neutron emission is a little bit different. Adding on to this, you're basically adding the, let's see, still some strong excitation energy, but now you have fission fragments that are moving on top of the Maxwellian description. And so more sophisticated, still a nice analytic way to get the average energy of the spectrum. And you can go on from here, now that you're describing the fission fragment, the fission fragment kinetic energies, you can go on to describe both fragments if you want in a two-part Watt function for the light and the heavy fragments here, as was done by Korniloff. And so this is an improvement on the Maxwellian, but still relatively insufficient for describing the details of the PFNS. It works better for low energies, but especially as you get into multi-chance fission and pre-equilibrium neutron emission, it's not going to do it. And so then we get into much more complicated models like the Los Alamos model, which doesn't have a simple form for me to just write down and say, this is the Los Alamos model. You kind of have to go through and describe each piece of the model and how it goes through. And so I want to make sure I point out this reference here if you want to know more, as well as Patrick's book, which is referenced at least 5 times, I think, throughout the course of this presentation. I'm not an author, so I can do that. And yeah, so reference this Madeline Znick's paper as well for the original description of it. But in short, you have a Weisskopf statistical neutron evaporation in the center mass frame, where you have now the center of mass, neutron kinetic energy, cross-section for compound nucleus formation, residual temperature after neutron emission, and also a normalization factor here is a function of temperature. And so then from this, you can estimate an excitation energy based on Q values, neutron separation energy, incident energy, and kinetic energy, average. And so these are kind of quantities that you can use to estimate the excitation energy, which then you need in order to understand the other properties of emission from the fissioning system. You can estimate your fragment kinetic energy per nucleon using a ratio of the masses and the original mass and the kinetic energies, the average total kinetic energy. And then if you know the average gamma energy and also the average neutron energy, you could estimate nu bar. And so now you're able to get all of these kinds of quantities out of one model. But as I said, it's not one equation that you can really write out. It's a collection. And this is even a very incomplete description of what the model does. And it is extendable, though, to multi-chance fission and pre-equilibrium neutron emission. So that makes it a very large step above any of these other models that we use to describe the PFNS. These are not predictive models. These are just models that we use to tell you what the shape is in a more functional form, basically. In a lot of cases, the spectrum itself isn't what's of interest to applications. It's the average neutron energies. So I'm showing here a collection of average neutron energies for PU9, U5, and U8 from the KINU project. Black, red, blue, PU9, U5, U8. and also end of fate average energy spectra as the different colored lines. And yeah, as you see, you get, just as we saw yesterday, you get an increase when you have just first chance fission available, an increase in the average energy followed by a decrease as you get this pre-fission neutron from second chance fission, and then another increase as you get towards third chance fission. And one thing you notice is that in the last 5 or so years, we've learned a lot about which nuclei have third chance fission, second chance fission, and what's the relative magnitude of those different processes. These are things that were not well known before, 5 years or so ago or so. And so we expected, for example, PU9 had some reasonable chance for third chance fission. Turns out not very much. And so that was an important change in our knowledge in the last number of years. Uranium isotopes, though, tend to have average lower kinetic energy as we expected. They actually agree much better with each other than we thought. And the relative chances of third chance fission are actually pretty similar as well. So in a lot of cases for an application, you might not, despite our efforts to make the most precise and beautiful PFNS that we can, a lot of times in applications that just gets crumpled into an average energy, and that's what goes into your calculation. But we still learn a lot about the fissioning process by measuring these spectra in as much detail as we can, and also things like neutron multiplicity. So I'll tell you what these labels are. You don't have to read them. These are now average neutron multiplicities measured from in 1969 for U5, U8, and PU9. And the trend here that we expect is as you increase incident energy on the x-axis here, you get more excitation energy in the system, therefore more energy available for neutron emission. And so you get this trend here of increasing neutron number as a function of incident neutron energy. Yeah, when thinking about these things, I usually go back to this equation. You can see now that nu bar is correlated with the excitation energy and the gamma energy, and also the average energy of the neutron emission. So I'll reference this kind of relationship a lot. Okay. You can also see that nu bar varies with things like the fragment mass. As you get close to, so these are fragment mass distributions on the x-axis on the left-hand side and TKE on the x-axis on the right-hand side from this Aladili paper in 2020. And keep in mind that when you're undergoing a fission fragment, when you have a fission event, you have to kind of sample mirror places on these distributions. So to make the total mass be equal to the initial mass. And so if you're on this side of the light fragment, you have to be on this side of the heavy fragment, this side of the light fragment, this side of the heavy fragment. As you get closer and closer to this region where you're entering closed shells in the nuclei from the fragments, you get more and more internal excitation energy before this turns mostly into kinetic energy. And so the light fragment tends to emit more neutrons until you get to a point where that's not the case anymore. And then the same is true for the heavy fragment. As you get away from these closed shell, more deformed, highly excited nuclei, you get more chances to emit, you get more probability, a higher probability to emit fission neutrons because you have a higher excitation energy intrinsic to the system. And then same trend over here, we just saw neutron numbers anti-correlated, should be anti-correlated to the total kinetic energy because they're proportional to each other. And so as you get increasing kinetic energy, you get decreasing neutron number, and so life makes sense because more of the energy is going towards kinetic instead of excitation energy, which is what you need to emit the neutrons. So property-wise, that's generally how this works. Neutron multiplicity, so it's not just the average neutron number, there's also the distribution of how many neutrons you emitted with fission. And so I'm showing here a couple of data sets that were compiled into this 2010 Tudor paper with some point-by-point calculations. Just to show you the distribution of what these, some examples of what these distributions look like. U5 thermal neutron fission and PU9 thermal neutron induced fission. Generally, the P of nu distributions will peak around 2 to 3. In most cases, slightly higher for PU9 than for uranium isotopes. And so ideally, when you measure these distributions, you'd like to get all of the data points, including the zeros, so that you can just have a measurement of the distribution. In practice, if you get enough data points to be able to describe the factorial moments of the distribution, that can be enough. And so what we have down here is a description of the different factorial moments for these P of nu distributions. And you can plug yourself in to get these numbers out. But what you get with the first factorial moment is the average, nu bar. Second moment gives you the width. Third moment here gives you a description of the skew, meaning how much of the distribution is towards one tail versus the other. And the fourth moment here, which I didn't write out, but you can figure out what it looks like, is the kurtosis. So basically how flat or pointed the distribution is. And so between these four numbers, you can get a pretty good description of what the P of nu distribution looks like. Yeah, and they're important because you could have, for example, a distribution that had the same mean, same width, same skew, but very different kurtosis numbers, and that would mean a very different distribution. For example, if you had a triangular distribution, it's peaked at the same mean, has the same width, skew would be 0 if it's symmetric, but the kurtosis would be very different than a square distribution where you have the same mean, same width. Still skew 0, but kurtosis would be very different. So these are all important to describe these different distributions. Yes?
Yeah, how do you practically measure these moments, and why is it easier than just measuring the multiplicity in the first place?
I've asked that question myself. It seems like once you've gotten to the point of getting a good description of these moments, you probably have most of the distribution anyway. And so then why don't you just report the data points themselves? I think in practice people do both. But yeah, they're both useful descriptions of the distribution. But if you've gotten to the kurtosis, you probably have most of the distribution anyway. Okay. And then, let's see, in the last 10 minutes, I think, before break, prompt fission gamma spectra, we talked about the different kind of regimes of gamma emission. First, you emit kind of higher energy statistical distributions of gammas, so less structure but higher energies. And then once you get down to the ERAS line, you're going along this line of minimum excitation energy for a given spin. And now you're going into more level-to-level transitions. And so we expect these gamma rays to be emitted first, and then these ones second, where you see a lot more structure that you can maybe even point to and say, I know what this distribution is. If you've measured it with, for example, a germanium detector, like at the, I'm blanking on the argon gamma detector name. Anyway, so gammasphere, geez. So if you've measured these gamma rays with something like gammasphere or another germanium setup, then you'd be able to identify different transitions possibly. Interestingly, in opposition to the prompt fission neutron spectrum, the prompt fission gamma spectrum shows a lot less dramatic variation with incident energy. And so these two spectra here, in green is uranium-235 neutron-induced fission at 1.7 MeV, and in blue is 15.6 MeV. Same over here. This is number of gamma rays per fission. So so really we don't expect a lot of difference in the spectrum as opposed to the neutron spectrum, where we really want to know what happens as you cross over these different thresholds for second chance fission, third chance fission per equilibrium, creates dramatic differences in the neutron spectrum. That's not generally the case with the prompt fission gamma spectrum, though there are differences. But there's been a lot less detailed structural detailed measurements of these kinds of spectra than for the neutron spectrum, partially because of its relative importance for applications, I'm assuming, and also just because there's not that much, it's not as exciting. There are generally more gamma rays emitted than neutrons, and so, then the gamma rays follow the same kind of patterns as neutrons in terms of relationship to fragment mass. And so for the same arguments of why we got a sawtooth pattern for the neutron number as a function of fragment mass, you also get a sawtooth pattern for the gamma ray number as a function of the fragment mass. More excitation energy, more neutron and gamma emission. You also notice here that there's an anti-correlation between the average gamma energy anti-correlation between the average gamma energy and the average gamma multiplicity. So if you have a very small number of gammas emitted, it's more likely that you had a few very high energy gamma rays that came out of your fissioning nuclei. And so there's an anti-correlation here. And then we also see similar patterns of excitation energy going up, number of gamma rays goes up. And then here I'm showing just some model calculations, some experimental data with some model calculations for a CGMF, FRI, and FIFRLN, which I'll describe in the last slide before the break here. Okay, and then this isn't the last slide. And then just as we had P of nu distributions, we have P of gamma distributions. And again, like I said, the average number of gammas is much higher typically than the number of neutrons, typically in the order of 5 to 7, as opposed to 2 to 3, or maybe a little above 3 for, or even higher at higher incident energies for neutrons. And so this is generally how you would observe a gamma multiplicity distribution, which is then you can describe via these same moments as we described for the P of nu distributions, but I'll also point out that this is well described by a negative two Poisson distributions or a negative binomial distribution, which is shown here. I'm not going to go into the details of how to calculate all of this, but this is a functional form that you can use to get a good handle on how to describe your probability gamma probability distribution. Okay. So the neutrons and gammas are all correlated with all the other fragment properties, the mass, the TKE, the TXE, all these things, and they're correlated with each other, not surprisingly, because they kind of compete for removing this excitation energy and getting the system, your fission fragment, back to its desired low energy state. And so on the left-hand side here, we have neutron-neutron correlations. And so one thing you see here is that they're peaked at 180 and 0 degrees with detecting two neutrons towards 0 degrees is difficult because of crosstalk probabilities for the detectors, and so that's why this gray region is here. But the neutrons are boosted in the direction of the fission fragments, and so you expect neutrons to either be in opposing directions or in the same direction predominantly. And so this 90-degree region, we expect it to be relatively low in terms of relative probability, and it is so. And over here, these are now correlations of the neutron number and the gamma number for MCMP Polemi calculations, CGMF, and FIESTA. And so one thing you see here is that, you can see these different anti-correlation patterns, again, pointing towards the competition for particle emission to get rid of this excess excitation energy in the nucleus to get it back down to its happy ground state. These correlations also come through in energy patterns. And even a qualitative measurement of these kinds of patterns can give you a good feeling for something that might be important for something like active interrogation scenarios where someone has an unknown container and you want to know what's in it. These kinds of things you can measure, and if you know what you're looking for and what pattern you should expect for different materials, this can help you quite a bit. And so, for example, here we see neutron energy spectra with gamma energy spectra. And it's very much not smooth. There are structures here, different gamma energies corresponding to different neutron energies, and I'll point you towards this paper here to get a more detailed understanding of where this comes from. But this is important qualitative information for us as well, and also helps us understand the fission process through our models and informs our models. So I want to make sure I describe these generators here. These have been mentioned a number of times through FIESTA, and if you want to see a very detailed description of a pretty detailed description of what all these models do, with a lot of references that give you a very detailed description of what these models do, again, go to Patrick and Ramota's book. If you anyone from the school takes one thing away from this slide, it is that this is pronounced Freya. It is not Freya. Yes. And if you go anywhere, public or not public, and Ramona is in the audience or near you and you say Freya, she will yell Freya at you. This has never happened to me before. These are the four main event generators, monocular event generators that we use to compare fission observables pretty frequently. They're similar, most of them are similar in lots of ways, but they have different approaches to how they solve different problems. So let's see. One important point though is that each of these codes takes input, mass, and charge distributions. These are not calculated. They are input distributions for the calculations themselves. And then the total kinetic energy is sampled after those are determined. From there, you need to determine your excitation energy and how it's shared between the fragments, and then how the neutron and gamma emission follows. And it's in those choices that the different models take slightly different paths. For example, CGMF shares the, TXE is determined by the Q value, and then there's a light-heavy nu relationship that is used to describe how many neutrons each fragment emits. And then the probability of neutron and gamma emission is sampled at each step with a different J-pi configuration. I won't go through all this in a ton of detail, but instead of this ratio, FIESTA, for example, uses this other parameter, RT min-max. And a lot of things are analogous, but with different usage. And then FIESTA uses very similar to CGMF and FIESTA, except that now we're looking at the light and heavy fragments modified by statistical excitation energies, thermal fluctuations are considered, and it assumes pure neutron emission until the excitation energy is below this neutron separation energy. And then GEF is different. GEF is fundamentally different than the other parameters. It's more of a general code, and to be honest, I'm not able to give a clear description of what this does and why and how it's different. So perhaps I'm getting a smile from Jorgen, so perhaps you can describe it more in your lecture. Yeah? Okay. All right. So, but these are referenced a lot in fission comparisons, and so I just wanted to make sure that this is clear kind of what these are. They are event generators. They're not necessarily nuclear models, but we can compare with them to make sure to see how well we understand the fission event and what we see from it. Okay, so just and one other point I want to make is that all these event generators produce different. That's fast, 3 minutes. All these event generators produce different results, and so we still see the same kind of sawtooth pattern with number of neutrons as a function of mass. We see P of nu distributions, but they are pretty different from each other depending on the choices that are made, and so measurements can inform how these models, the data that these models should produce. And there's a limited and different number of ways that these can be tweaked to reproduce the observations, but that is it's much longer and detailed conversation than we have time for here. But you will see, and you'll see all those event generators described throughout the course of, you saw it already, and you'll see it later on in FIESTA, I'm sure. So some take-home messages before the break. Many decades later, even though we have been measuring fission since just before the Manhattan Project, and since then pretty heavily, there's still a lot to be known. These models do not describe our understanding of fission neutron gamma emission, much less all the other aspects of fission, and so measurements are still required. And even for things like CGMF, FRIA, FIFRLN, and GEF, you still need these input distributions to start the calculations. And even if average quantities are of interest, for example, this average neutron energy, sometimes, like I said, that's all that really goes into a lot of calculations. The spectra themselves tell you a lot about the fission process, which goes into the models, which then describe the PFNS for the evaluations. So all these things are connected, and so you're not fighting a losing game by measuring the spectrum or these fine details of the neutron and gamma emission correlated to other quantities. It's not a losing game, even if that number doesn't go into a calculation, it informed it, and so it was important. And also that goes a lot towards our more pure desire as physicists to understand this fission process. The more details we understand and we can measure, the more we can understand the process and get closer to actually knowing what's happening here. So that'll be the end of the first session. Thank you, and I'll take any other questions now.
Well, my question is towards the second point you have there. If you look at the PFNS, how can you constrain the models since your neutron, you don't know if they are from pre-fission or post-fission?
Well, you can do, this is a good way of how to constrain the models. So this is, again, the average energy, but if you look at the spectra, you can see that there's very big differences. These are evaluation results, and so what this told us was that the relative probabilities of these different chances of fission, and therefore the internuclear models, how you should weigh these different processes, that's what we're kind of informing. And also thresholds for when these occur, that wasn't very well known until 5-10 years ago. So there's lots of things you can understand from just the neutron spectrum. Yeah.
Hi, thank you. This was a great first part of the talk. I'm excited for the second part. I know you mentioned that for gamma multiplicities, there are a lot of considerations. It's a longer discussion to make that curve, the probability of the gamma multiplicity. But I'm wondering, like, maybe just on a very high level, what do you decide, like how do you decide, say, coincidence time or total gamma energy deposition, or there are just a lot of different things experimentally, right, that go into that?
Yep. Yeah, so in the second part, we'll talk about differences between differential and integral gamma and neutron experiments and correlated experiments and how these things work. So maybe we should, if I haven't answered your question by the end of the second session, ask it again.
Oh.
Yeah.
Yeah, this was a great introduction. I just want to make a couple of comments about the event generator, the codes.
Sure, please.
I think it's important to also emphasize that some of these, or most of these codes also take nuclear structure models as inputs. It's not just the yields, and you also have a model for level densities, you have a model for gamma strength functions, transmission coefficients, and that also explains some of the differences perhaps that you see in the predictions. But both from experimentalists and theorists, being aware that these nuclear structure models are involved when you do this fission calculation, and this is as well, I think.
Yes, very good points, thank you.
So, can you explain more the plot that you put of energy of the neutron versus gamma energy? For me, it's not that clear why you have like some structure there, because in the end, you don't know exactly from which fragment it comes, the neutrons or the gamma. So then there could be different fragments.
So,
not making you that clear.
yeah, qualitatively observing the structures, why are there structures at all? I think it relates more to the spin parity of the states that are being populated after the fissioning system itself. And before I ramble, I'm just going to say I'm going to show this paper to you during the break, and we can talk about it.
Yeah, I would like to see.
Okay. Yep.
Any other questions before the break? No? Okay. Well, mini break then?
Mini break? Yep. Thank you.
Okay, let's start again. Okay, great. Excited to have you on part 2.
Okay. So before I start again, just a quick reminder on where we were and where we're headed. That was kind of our crash course on observables, general properties of why they look the way they do, neutron multiplicities, gamma distributions, correlations between these different particles in energy and number, and also the event generators, a brief description of them since you'll see them a lot in fission research in general, and some models to describe the PFNS and gamma distributions. Now this second session is going to be more for experimental techniques and pitfalls and things like that that can, oh, thank you so much. Self-service. So yeah, starting off, you have neutrons coming in to, you want to measure the neutron spectrum, you have some kind of fission detector probably. The kinds of fission detectors were, fission counting targets were covered a lot in the first day or two, and more so in the last, we've covered this a number of times. So you're going to have some kind of fission detector, and you would like to measure the neutrons in coincidence with a fission event. Depending on your fission detector, you'll have different amounts of information about the fissioning system. But one thing that is consistent across all kinds of fission neutron coincidence measurements is that you really need to have as high of an efficiency for your fission detector as possible. No matter what anyone tells you, unless they have a piece of actinide floating freely in the middle, very thin, floating freely in the middle of an ionization chamber, you're missing some fragments. Your efficiency is never 100%. And that's partially because you usually have actinides deposited on some kind of plate. And so if you imagine your fission axis being along that plate, you're not getting those fragments that are entering your ionization region. You're always missing those. And then it's a question of, okay, at what point does the fragment reach enough of the ionization region to give me enough of a signal to actually see the fragment? And maybe for the heaviest, highest charge, or highest kinetic energy fragments, you'll see those when they just start getting into the ionization regions, but maybe for the low excitation, low charge ones, you don't. And so there's a distribution of where you start actually seeing your fragments from your fission event. And so that's an angle dependence of the fission detection efficiency. A lot of these detectors don't measure that, and it's very hard to do that. There are some detectors that measure the mass and the charge and all of these things very, very well. These are also generally very hard and cumbersome and low efficiency to put into an MEV neutron beam, 1 to 20 MeV. That's why you don't see a lot of these measurements. All these very nice sawtooth patterns, or I shouldn't say all, a lot of these very nice sawtooth patterns and other distributions that you see, a lot of them you'll notice are at spontaneous fission or thermal neutron-induced fission, because it's very easy to measure these, or it's a lot easier to measure these quantities. It's very hard still, but it's a lot easier to measure these quantities in that kind of energy regime than it is at the 10, 15, 20 MeV range. And so what this will do to your neutron spectrum then is that because of this correlation between the fragment emission angle and your neutron angle, you'll get an energy dependence. So let's say your fission detector doesn't tell you the angle of your fragments. You just see fission events. You see alphas, and you say, I'm going to characterize my alpha contamination in my fissions, and I'm going to cut on my fissions and see how many I lost based on my distribution. and you assume you got all of them, but really you missed some because your efficiency isn't 100%. They didn't show up in your spectrum at all. And what this will do then is, instead of being able to measure the angle of your fragments, what you can do is look at the neutron spectrum. And so if you have a deficiency at 90 degrees, which as I said, all ionization chambers will, because the fragments emitted along that direction will not be detected, you'll see a decrease in your neutron energy spectrum. And then conversely, on the outer sides, you'll see an increase in the energy spectrum. And that's because the highest energy neutrons you see from your fission event are the ones that are emitted along the fission axis. They're boosted by the fragment, and the ones that are emitted along the axis will get an extra boost. And so those are the ones that are the highest energy neutrons you'll see. You can also have neutrons emitted backwards and to the sides, but those have less of a boost. And so since you're missing these neutrons near 90 degrees, you'll see a reduction in your average neutron energy. Conversely, at the outer angles, you have fewer of these neutrons emitted at 90 degrees that were boosted less towards your outer detectors. And so you'll miss some of that low energy neutron spectrum that you should have gotten. And so really the correct answer for this example spectrum is right around here. So you get an excess at outward angles and a decrease in inward angles. And so over here, this is a correlation pattern of fission fragment emission angle and neutron energy measurements. And so for differential experiments, we have a detector placed at different angles. You'll only see those neutrons at certain positions. And so that's what these large red patterns are. This is where the detectors are in this particular experiment. And so you take this kind of pattern in here for your fragment emission angle. This turns out is from correlating CGMF calculations into MCMP and then resolving MCMP with experimental features, getting you to a lot of details that I just brushed over this spectrum, which then you can use to characterize, okay, what if I have an efficiency spectrum that has a dip around 90 and comes out this way? What kind of pattern do I see in the energy spectra? So this is a big problem with fission neutron experiments that needs to be characterized, and there are ways to handle it, like with this. Yes?
So this dip you see at 90 degrees, that's not anything to do with like neutron detection efficiency, that's just your fission detection efficiency that you can't detect it.
Yep, yeah. Okay. Moving past the fission component, the fission detecting component of the neutron experiments. Depending on your experiment, you might be interested in using one of these kinds of detectors. And they all have different properties, and so you kind of have to pick and choose your favorites for what you want to do. Liquid scintillators, we've seen a lot of data from liquid scintillators. The Kainu high energy data points, the CEA Vendetta, are all liquid scintillators. These are nice in that they detect via hydrogen and carbon scattering. This is a pro and a con. So some detectors detect neutrons via scattering, some via capture. If you detect a neutron via capture, once you see that neutron, it's gone. You never saw it again, and it might have done something else before it got to your detector, but once you captured it, it's gone. When you use these liquid scintillators or plastic scintillators or anything else that uses scattering as the detection mechanism, now you have to worry about, did you see the same neutron twice or 3 times, or did you do something else? Maybe it scattered off the floor, then a detector frame detector, and so you saw it twice in a different way. Lots of things can happen, and so this all goes into neutron environmental response that I'll describe in the next slide or so. So these are generally good for higher energy, higher energy neutrons, and they have N-gamma PSD capabilities, so you have up to some limits in ability to separate out neutrons and gamma rays. So that also makes them really attractive. Lithium glass detectors are also really common. These have a large thermal neutron capture cross-section, and so for low energy neutrons, you can have a high chance of detecting them. Moreover, you have a high Q value, a little over some 4.44 MeV or so. It's a little bit higher than that. But you have a very large Q value so that when you capture this neutron, instead of getting a tiny little signal like you would from scattering, you get a massive energy release every time you capture this one neutron. So you see them well above background. And you can get very good measurements of neutrons that you capture via lithium-6 and T all the way down to low energies and get them well above your random backgrounds. Plastic scintillator and timing is also a consideration for a lot of these detectors as well. Plastic scintillators also have fast timing like liquid scintillators. Lithium glass detectors aren't slow, but liquids are faster. They also have PSD capabilities, and in a lot of ways, these can be kind of swapped out in some sense. They do have slightly different pros and cons. There was an experiment that used a uranium-235 fission chamber to detect the neutrons as a neutron detector, which is great. I thought that was a really smart idea. I thought about this myself and then read the paper and I said, oh, this has actually been done because the U5 fission cross-section is a standard up to a certain energy. So we think we know this efficiency pretty well, and as long as you understand your fission detection efficiency, you should have a pretty well described neutron detector. Proton recoil telescopes operate about the same way. Julian mentioned this the other day as a way to mention the Californium spectrum, using proton recoil telescopes so that when you see a neutron, you understand the NP scattering reaction very well. Now you understand a lot about your response of your detector. And you're not worried about whether or not you understand this lithium-6 NT reaction or carbon scattering. You're relying on something that we should know very well, NP scattering. So these are typically, not always, but usually used in differential experiments, liquid scintillators, not always, but they also have, there have also been used doped scintillator tanks, these large tanks, where you're not worried so much now about measuring. Yes, question? Thanks for waiting for the microphone.
Yeah, I have a question of the fission chamber. When you make a lot of background, no? Because you generate a lot of neutrons.
So you'd be surprised at, in an in-beam experiment, you're more worried about, when you're blasting it with neutrons, you're more worried about the neutrons that scatter around in your environment. You're less worried about the neutrons from the fission. But yeah, that's a good point. If you had a bunch of neutron detectors around this fission detector, it's making neutrons that you could detect, and so that's something you have to worry about. In this particular experiment, it was a fission chamber, not a whole array of them. Yeah. If there was an array, then you'd have to worry about that for sure. Good point. So there's another realm of neutron detectors, these high efficiency large detectors where you're not so worried about the energy anymore. You just want to make sure that when a neutron was emitted, you saw it. So you want to count neutrons basically. And so for these, you generally have scintillator tanks doped with something with a high thermal neutron capture cross section like gadolinium 155 or 157. And so these are very slow because you need the neutron to moderate in your environment on the order of microseconds or if not milliseconds before they capture. But you should have a very good efficiency. And helium-3 gas tubes generally work the same way. You can organize them in an orientation with some polyethylene or something else to slow the neutrons down before they capture onto the helium-3 in your detector and give you a good counting of the neutrons. So this is a short reference list of what neutron detectors you might be interested in depending on your measurement. Some recent measurements we heard about, so there's a whole series of Kainu papers on PFNS that we saw referenced some yesterday, and I've shown some today. Also from our CA collaborators, Chatillon and Paolo Marini, have measurements of the plutonium-239 PFNS, Sarday 2013, and we've seen recently some results from CA folks about U5 and U8 PFNS as well, ongoing towards Pu240 and other nuclei. So there's been a lot of measurements lately. Most of them have been coming from Lance, from Los Alamos and CEA. And so in recent years, this is mostly what we're looking at, though certainly not the only measurements of interest, of course. And there's lots of measurements in the past. I'm just pointing out the most recent examples here. So this is the Kainu neutron detector array that, for those that took the tour, it was up on the flight path when you walked in there. This is an older version of Kainu called Figaro, also liquid scintillators, that was meant for inelastic scattering measurements, but was applied to the Chatillon measurement of plutonium-239 PFNS. There's also been measurements using highly collimated neutron detectors and monoenergetic beams so that we can understand what the incident energy was without worrying about this correlating the time of flight with the fission timing and all of these things. And so this is another example. There's paraterfinal detectors surrounded by lead. And so these are just some examples of what an experiment might look like. But to get a more general view, Denise has mentioned, there's been some mention of templates of how we describe different experiments. And there is a template paper from Denise in 2023 describing the PFNS. And so this is a general description of what a PFNS measurement analysis or the main components might look like. You have your counts. This is your chi is what we're going to usually use to describe the PFNS or to denote the PFNS. It's a function of the incident and the outgoing energy. This is a 2D matrix. Kind of like when you measure a cross section for an incident energy, you get a data point. For the PFNS, when you measure an energy, you get a spectrum. And so it's a 2D quantity, and you want to map that out as a function of the incident energy. And so you have your counts, your background, dead time correction perhaps, angular distribution effects. The fragments will have angular distributions associated with them relative to the incident neutron beam. And you'll see patterns of that in your neutron spectra. And so you need to worry about that kind of effect. And then there's efficiency and multiple scattering. And so this I'm going to talk about a little bit because this is a big part of neutron detection experiments in general, not just PFNS. You want to understand these are typically separated into two different quantities. In my mind, they are one and the same because they're so tightly correlated. And the reason is that when you emit a neutron, this is a PFNS neutron energy on the y-axis, you get a measurement of the time of flight of that neutron. This is a distribution. Depending on your environment, this will look the same. This is for EJ309 liquid scintillators in the Kainu experiment. And so along this line, you had neutrons that left your detector, left your fission event, went to your detector, and were detected at a time of flight corresponding to the actual neutron energy. However, all of these other neutrons did something else more nefarious, and they were scattering off of objects in your environment or going from detector to detector. And all of these things go into your environmental neutron response. So there's a quantity called the efficiency that we think of as a 1D quantity. You measure it with californium or something else. And then there's the environmental response, which takes into account the fact that if you measure your efficiency with californium and then switch to a different chamber, that's not the same environment anymore, and your efficiency might not actually apply. Or if you take a detector to a monoenergetic beam, put it and measure the efficiency, and then take that detector and put it into an array somewhere else, that efficiency might not apply because it really matters what's around your environment, which is why we have these experiments with these highly collimated neutron detectors trying to get around this, so that when you know the efficiency, you're reducing the scattering as much as possible. Or if you're in this in-between region where you have a differential experiment with scattering involved, you just have to understand what the scattering looks like and how to account for it. And so for that reason, I say that efficiency and multiple scattering are pretty closely related. This is now the same kind of response matrix for a lithium glass detector. And again, you see lots of different structures. Now you're looking at different resonance features in the detection cross-sections or reactions of materials in your environment. In an experiment, you would never see this. You would just see a spectrum that looks relatively smooth, kind of like this, except you have this large resonance from lithium-6Nt at about 244 keV. But these things are happening in your environment, and so you need to understand what they're doing to your spectrum and how your observation of the spectrum is influenced by how the spectrum itself changed throughout the course of the experiments. This process of the neutrons scattering in your environment is generally called downscattering, which I said there, which makes you think that you're scattering down in energy, which is true. You have a different time of flight, which is observed as a low energy, and your neutron also lost some different amount of energy. So the time that it took for the neutron to get there, the energy that it got there with, and the energy that it left the detector with, that's three different energies that you could interpret as the actual neutron energy. And you want the correct one from the sample. And this can do some strange things. You call it downscattering, but it can actually produce high energy excesses above different features in your response. In lithium-6, for example, we have this nice large resonance. And if you have higher energy neutrons that took a time to get to your detector corresponding to, say, 400 keV, but actually had an energy on the resonance, then you'll get a higher efficiency for detecting them. And you can see this as a broadening of your spectrum. You see it very clearly on resonances, and so this kind of resonance is a blessing and a curse because it shows you this thing, but it also means you need to understand this very, very well. And so you can see very fine details like this as evidence for, yes, there is scattering happening in your environment, and it's distorting your spectrum. So neutrons are difficult. I say that you don't, with charged particles and other kinds of particles, you can kind of direct them and tell them what to do so that you get them to tell you the information that you want. With neutrons, it's more of a relationship, and you kind of just let them do what they do and then figure it out afterwards. So that's how I kind of interpret them in my head. And so because of this kind of response effects, I want to describe kind of what this can do to a neutron spectrum measurement. And so let's see. This is a 2D matrix for a bunch of measured spectra and reference spectra. Over here, this is uranium-235, PFNS at thermal, 7 MeV and 14 MeV. So first chance fission, first and second, first, second, third in pre-equilibrium. So the spectrum looks very different, and the spectra on this axis are shown in the diagonal, so you can see how different they can be. Over here is a californium, and then a quantity that you'll have to read a paper to read more about, to learn more about. So this is the californium spectrum here. And so if you were to use, for this simulation of the Kainu experiment, use californium to extract the PFNS of, for example, U5 at thermal 7 MeV or 14 MeV, then the black line here is the ratio of what you would measure to the true spectrum. And so, let's see. So along this line, you have the same reference spectrum. So now this is the same spectrum over here, U5 thermal, 7 and 14 MeV, and this is your reference spectrum. So really we're going to focus on this line right here, where you have U5 thermal relative to californium. And the black line shows, okay, you're relatively close to unity. Things aren't terrible. A californium spectrum looks a lot like a thermal neutron-induced U5 spectrum, and so the efficiency or the response is pretty similar. When you start introducing second chance fission features, now you have some pretty noticeable differences upwards on the order of 5% for the analysis done in the simulation. And then when you introduce peaks in the spectrum, like from pre-equilibrium, things go all haywire because there's no peaks in the californium neutron spectrum. And that does something very different to your response. And so you start to see some very big differences. Here's something interesting that relates back to Toby's talk from yesterday, is that if instead you inverted the process, we can do this in simulations because, like in theories, we know everything. So we can take your simulation, we know what the input spectrum was for U5 thermal or U5 7 MeV, and we know what the californium spectrum looks like from our simulated analysis. Now let's invert the process. Let's say we're using U5 at 7 MeV as a reference for californium. You do that same process and you'll find that you have the inverse problem here. Your ratio of the californium in the blue line here to the unity gives you the kind of the inverse. And so you can use this as a correction to the californium spectrum. And if you understand the response matrix, you can actually do this in an experiment without knowing what the input spectrum is. You measure the spectrum, you assume that your answer is correct, and then use that as a reference for your californium. And you'll get the wrong answer unless you have a very low scattering, well understood 1D efficiency environment. And when you apply that correction to californium, the equation you reach is actually the exact same gold unfolding or iterative unfolding equation that Toby showed yesterday, which is very cool. This is a result from this paper that we looked into how this response impacts 1D uses of 1D references for PFNS distributions. So it's all to say this is complicated, and that's all just for standard PFNS measurements. There are lots of non-standard PFNS measurements that are much more exciting. For example, the Lestone NUX experiment was measured at a nuclear test. And so you had a very high neutron flux where you could do lots of cool things. And for example, you can charge exchange neutrons for protons and look at neutrons on a Faraday cup and get a very high energy or high precision measurement of the PFNS. This, so Lestone and Shores measured the PFNS for U5 and PU9 at an average incident energy of 1.5 MeV. And these two measurements form really a good basis for our understanding of these two PFNS distributions for those two nuclei still to this day because of how high statistics they are and how well we think we understand the experiment. Hey, fun scavenger hunt for anyone at the Bradbury tonight. This is somewhere in the Bradbury in an actual mock-up. See if you can find it. I went there for 3 years and never knew it was there and then found it. So let me know if you find it. Other non-differential experiments, you can, like I said, use fission chambers to measure the PFNS, like was done for a California measurement by Blinoff using U5 fission chambers. You can also use proton recoil telescopes. This is, I call it non-standard because it's not typically done because of the low efficiency of the proton recoil telescopes, but you can certainly do it, and it can give you a good understanding of the spectrum. And also I want to mention Chalupka, that they, in order to reduce neutron backgrounds at higher energies, they went under a mine in Australia to try to get as low background as possible. So people have done some pretty interesting things to get the PFNS. Okay, and I want to mention one thing. I'm not going to spend too much time on this because I think I spent a lot of time on the other slides, but we'll talk about more about covariances tomorrow. But this gets back to what the meaning of the PFNS actually is, and it's the PFNS itself is a shape. It's a probability distribution. And so when you want to understand what the PFNS means, really the y-axis doesn't matter. What matters is the ratio of the different points. And so that ends up having an interesting correlation to the covariance that you could, and in my opinion, should derive for your results. If, for example, for the Chi-Nu results, we have two different data sets. One for liquid scintillators, we have a covariance, and lithium glass detectors, we have a covariance. And we want to combine these into a single shape, as we've done. This then gets you to a point where you need to describe the relative values of the PFNS at each point. It's not the magnitude that matters anymore. It's the relative values that matters. And so this is the difference between a shape and a normalization procedure where you're actually considering all the data points together having the same area and propagating the covariance through that via this equation right here, as opposed to a scaling where you take each data point and just move them up or move them down. Those are very different things. and they're used interchangeably a lot. And I don't know. I prefer the word, oh yikes. Okay. I prefer the word scaling for just shifting up and down. For newbar, like I said, you're looking more at these integrated experiments where you want to count the neutrons. And yes?
Can you go back to the first non-differential experiment? I don't understand. What is the experiment? The first, no, go back. Another one. Mass, that one.
This one.
Yeah. What is it? I don't understand.
Well, down here you have a compressed supercritical mass. You have a chemical explosive. This is a nuclear test. This is described in an openly released document, and it's described this way in an openly released way. And so to get more details about this, read this paper, and that's about as far as anything can go.
Okay.
Yeah.
For me, it's slide 43, I guess. No, 41, sorry. 41. Yeah. What are you showing there?
These are the correlation matrices for two different data sets and showing how the correlations change when you go through this normalization procedure to report the PFNS as a shape instead of an absolute magnitude quantity.
I don't understand the axis.
So we'll talk about correlations and covariances tomorrow. On the z-axis, this is a correlation of one data point to another. So of the data points in this measurement, add an incident energy, so these are different outgoing energy of the PFNS, how they relate to each other. High correlation means that when they're randomly varied, they tend to go with each other. Anti-correlated means they go in opposite directions more if you were to randomly sample from a data set. And so these kinds of correlations.
We'll see this tomorrow?
We'll see some more examples of this tomorrow, yeah.
I don't know what the unit there, data point number, why it's really not clear.
There are 65 data points in one of the data sets between the two detectors. So each data point number, it's confusing to, here's the energies up here. So these are different energies of the data shown for PFNS, two different detector types, lithium glass and liquid scintillators, and to plot them on an even scale to not have these logarithmic deformations of the correlation matrices to make it confusing to look at, we just looked at data point number instead of the alternative.
Yeah, I will have a look at the data.
Okay, sounds good. So I'm going to move a bit faster now. And these slides will be available later on as well. So newbar measurements, generally now you're not worried about the neutron differential energy. You're worried instead about just counting the neutrons. You want to make sure you have a high efficiency for detecting these neutrons as much as you can. And there is also another, and so yeah, basically also looking at another template paper about prompt newbar extraction. There's a similar pattern where you can look at the counts, backgrounds from gamma rays, and also an efficiency, dead time correction. And yeah, I'm not going to go through all this, I'm sorry, but please look at Denise's series of template papers. It's not just fission-related quantities, total cross-sections and other nuclear physics quantities as well. Very nice series from last year, so please have a look. And then, yeah, so those are two kind of regimes of neutron detection, newbar and differential neutron experiments. Now we're moving towards a regime where you can use differential experiments to get newbar. For example, from Marini et al. From the CEA, they use their measurement of the PU9 PFNS measured at chi-nu to get newbar as well, shown on the black data points here. And so if you understand the newbar from californium and the spectrum from californium and the overall efficiency of your detector system, and you can integrate everything out to all angles, you can get the total newbar of your spectrum. And so that's what's shown here. And yeah, I'm not going to describe this too much. So I will go forward. Anyone interested in anyone wanting to know more about P of nu measurements from differential experiments, please see Owen's poster in red on the back wall there. And so in general, I just want to point out that PFNS differential measurements and P of nu newbar measurements have very different requirements typically. So for energies, you want segmented detectors in different places with a well-known time of flight, and you want to be able to see what the energy was as a function of the incident energy. For neutron counting, P of nu, you typically want a high efficiency detector with a known incident energy, so you're not worried about time correlating things, you're just counting as they come out. And newbar is approaching recently this middle ground between the two, where you can do one or the other, or possibly all three. And so this is an exciting time for this. Briefly on gamma ray detectors, similar to neutron detectors, you have competing characteristics. Now you're worried more about gamma energy resolution. So when you think about gamma energy resolution, you're thinking about germanium detectors probably, where you have very good resolution. However, you have very long pulses, hundreds of microseconds long pulses. And so they're very slow, and their time resolution is generally pretty poor, very poor compared to neutron detectors, like liquid simulators. However, you can use trapezoidal filters and other things to get this pulse decay time to not be as big of an issue. But a lot of times the approach taken is to use a different kind of detector that is quite a bit faster, such as lanthanum bromide, cerium bromides, sodium iodide, barium fluorides, lanthanum chlorides, and BGO. And so I'm just listing here kind of characteristics of resolution, decay times, and different qualities. One feature that shows up in a number of detectors is intrinsic radioactivity, such as the barium fluoride detectors and the dance detector array at Los Alamos, at Lance. And so this can be really useful for understanding how your detector gain is drifting as a function of time, because if you can PSD gate on these radioactive components, you can see how they shift, and you can recalibrate all of your spectra based on that. So it's another thing that's kind of a blessing and a curse. And so it's something to consider in your choice of gamma detector. So some examples of prompt fission gamma spectra measurements here. These are both of dance, which I think it was closed yesterday, wasn't it? Yeah, so sorry I didn't get to see this. It's nice to see in person, but there have been some PFGS measurements at dance. I'm also showing here an example with a fission chamber and some, I believe these are lanthanum bromides in the corner. I may be misremembering this figure. And also some other experimental setups, just some examples here and the references for recent measurements. And you can see what people are doing. Some people are even taking combinations of barium fluorides, lanthanum bromides, and lanthanum bromide sodium iodide combos with an ionization chamber to get more inferences on the PFGS. So things get kind of complicated depending on the desire for your experiment. But in the same way with neutrons, you have this difference between spectroscopic measurements and counting measurements, number measurements. So for something like for an energy spectrum measurement, you would want to be able to have your detectors segmented so that you're not worried about having so much Compton scattering or total energy deposition in your experiments. So there's, again, different competing views of how you want to set up your experiment depending on what you want to get out. A lot of the experiments were actually measured close to 90 degrees or further out from it, or near that range, and so the angle might be a consideration factor as well. And I'm just reminding you here what the PFGS generally looks like. You have your high energy statistical gamma rays with some structure down at low energies as you get down to your ERAST band. And then for neutron numbers, again, you're looking at your higher efficiency detectors that maybe you're not so worried about the small structures of the spectrum, but you want to make sure you count all the gamma rays that you see. And so in this case, yeah, you can get out the total gamma ray energy spectra, and this is pre and post unfolding for the analysis that was done for this dance measurement by Shiz et al. In 2014, and also the gamma ray multiplicity distributions. And yeah, so one thing you'll notice is that, yeah, because you're not getting the differential energy spectra, you're not getting this very clean measurement of the energy of the gamma rays, you have this more smooth distribution. And so the black data points here are the unfolded distributions from the same Shiz et al. Paper compared to theoretical calculations where you see the structure. And yeah, just showing that this is all smeared out, showing the different environments and what you can get. And so you have to really worry about what you observed, what's the resolution, and if you want to go the step of using an integral experiment to get the spectra or vice versa, then you have to really worry about how well you understand the system in this way. And so, yeah, same kind of concepts. They're kind of analogous in a lot of ways, the neutron and gamma experiments. So I won't go too much into detail on this one. And then, I think I'm right at time here, outlook. Yeah, like I said, neutrons are the best part of fission. And without them, we would not be in this room, I don't think, or at least the interest in fission would look very different at minimum. And so fission, neutron, and gamma emission is also a very rich and active experimental area right now, especially neutron emission, PFNS and NUBAR and P of nu. People are pushing the boundaries and the borders in lots of different ways, and so we're always looking for new people to add new measurements and techniques to what we can do and what we know. And yeah, neutron and gamma ray emission, I didn't talk about correlated experiments in this section just because of time. But the previous FIESTA in 2017, the talks were more about thermal and spontaneous fission, getting to the point where you actually create a neutron spectrum. And so if you want to learn more about those kinds of details, I encourage you to look back at the 2017 FIESTA webpage at Josh Hamp's presentation, and there's a lot of good details there. And so here I'm trying to just add on to more of the high energy spectra on this. And yeah, there's no, as of right now, no good way to measure all of these quantities in a single experiment, but new experiments and ideas are happening every day, and so we're hoping that in the future this can be a reality. And then some references. That's all. Thank you.
Right, time for a few questions.
I have a question about the same plot that they were asking about, the correlation plot. So is the way I understand this, I just wanted to confirm if I'm understanding it correctly. So on the left plot that is, not this one, the one that they were asking about.
Oh, the correlation matrices, okay.
So you have like two disjoint experiment or like detector system, and the counts that you get from those are uncorrelated in the left-hand side plot. But I guess on the right-hand side, what's happening is that the constraint for the shape is introducing correlation between those data. Is that the right way to understand this?
Yep, so now that we're in the question session, I can take a little more time to describe this. So in Kinder experiments, we do two separate experiments. We have a lithium glass detector array for low energy neutrons and liquid scintillators for high energy neutrons. And so we have the same PPAC targets that we swap in neutron detectors to measure the two portions of the spectrum. And so yes, you perform two experiments, one with 44 data points and another with the remainder to get you to the top here. And so you have a covariance or a correlation matrix, which if you're unfamiliar with these and these are new words to you, you should be very excited about the practical session tomorrow because we'll talk all about it. But you have a correlation matrix for the lithium glass data set, independently analyzed, different beam, different time, different year. And then the same thing for the liquid scintillator data set. They have different analysis aspects that go into them, and they're effectively uncorrelated. And so you can set up a single matrix like this describing then, so there is an overlap region between them from 800 keV up to 1.5 MeV. And it's that connection between them that allows us to say we have a reference to make this a single shape across the entire energy range from 10 keV to 10 MeV. Okay, so then if you plug in all of your numbers, you end up with two spectra that are not actually lined up with each other. You want to scale one to the other. Well, that changes, say I scale the lithium glass detector up to the liquid scintillator. That leaves this one alone, but changes this one. Or let's say I make the other choice and I bring the liquid scintillator down to lithium glass. That has the opposite issue. And what this is pointing at is that really what we're trying to get to is the probability distribution of the PFNS. We want to know the shape, the relative value of the distribution at all of these energies. And so if you, a third choice might be to move them both and have them have the same average in that overlap region. It turns out if you consider the PFNS as a shape and you carry out this covariance normalization procedure as opposed to a scaling, you get this exact same correlation pattern no matter what you choose. You can move this one up here, this one down here, or move them both together, and you get the same exact answer because it's a probability distribution and all that matters is the relative points. And so that's what we did, and that's what this is reflecting. This is pre this calculation and this is post this calculation.
Any other questions? So, you want to?
Nice talk, Keegan. Just, I think that there are two comments that are relevant. The first thing is just to make sure that most of the Nubar experiments in the past, they were essentially done with 4 or 5 detectors, and they were independent of PFNS. The main reason for that was that to get a good Nubar from PFNS, you have to cover the whole energy range. Now, these days, with CA Los Alamos collaboration, I think we are getting there, but still there is uncertainty associated with the fact that you have to extrapolate, especially at the very beginning, because no matter the detector, even with the newest Vendetta detectors, you still don't go that low. So there is some uncertainty there associated that we have to assess. The second very important point is that if we are using those new bars, they are going to be correlated because you are getting new bars from the PFNS. And this is not considered in current libraries.
Oh, that's exciting, yeah. Anytime there's a new correlation to calculate, that's fun news. Yeah, for sure. As we get into, that's a very good point about the reason the integrated experiments are the way they are is because, yeah, you don't care about what the PFNS looks like. Everything, no matter the details of the shape, it all gets scattered and thermalized down into thermalized neutrons that are counted. And so yeah, the effort of integrating out the actual PFNS to get the full spectrum requires you to go to regions where you can't measure. And the PFNS in principle goes up to 20, 25 MeV. It's very, very small up there, but that part matters for Nubar, and it goes below 10 keV and below and on as well. And so yeah, you have to extrapolate. You have to rely on your reference and assume that your neutron scattering in your environment isn't throwing off your spectrum and therefore your integral. And yeah, there are ways that this can show that it's an issue in your analysis, and I agree that Nubar and PFNS will become correlated.
Okay, I think it's time to
Yep.
stop, but thank you again for a great overview.
Thank you.
Thank you.